Okay, good afternoon, everyone. So, previously we have discussed about the bar element and beam element, but now let's see if we are combining these two bar and beam element together, then we can able to get the frame element. And in that frame element, we will have like one equation. So there is a bar and beam element, both are coming together, but still they are decoupled, because you can see once we are solving for u, then there is no term of w. So in this there is no term of w, and here once we are solving there is no term of u. So there is no term for the u actually present. Okay, so therefore these two are the decoupled equation, and let's see how we can able to solve this. So once we are solving this, so we can get it phi j equal to this one. So this is my displacement field. Displacement field in axial, and this is my transverse displacement field. Transverse displacement field, and this is my rotational field. Okay, so we got that full thing. Now here our target is to forming the stiffness matrix or the spectral element matrix. So how we can able to do that? So we are first just substituting the x equal to 0 and x equal to L. So that left side and right side, we try to calculate it. So you have already seen that in case of the bar, you have seen. So this is just like we are just following the same procedure what we have done for the bar. We can able to get it like this. Same we are following for the view. So here we need to remember one thing. There is a small mistake. It should be minus sign. First one should be minus sign actually. Here there will be a minus sign, because that force will be changed. Because once we are having this, these are the degree of freedom and your forces will be like that. So these are the normal forces. So once we are doing for the first side, that one should be negative. And once we are doing for the beam, what happening? We are having the degree of freedom like this, but forces are positive like this. This is like this. Then this is like this, and this is like this. So you can see that our displacement cannot be negative. Displacements are always positive. So W0, WL, theta L, theta J. Well, the theta 0 and theta L. So these all are always positive side. Okay. But now once we are doing the bending moment and shear force, so in that bending moment you can see here we are having minus sign, because you see these two are not in the same direction. One is going clockwise and another is going anti-clockwise. That's a difference, and that's why we are having a minus sign here. But that V0 is positive. So you see there is a positive. That's not getting changed. Then ML, look, ML, this and this, that red and black, they are basically in the same direction. Okay, both are going anti-clockwise. So that is also positive. But these two velocity, these two shear forces, they are negative. So accordingly, so always we can think that if we are solving, like if in our differential equation, that like once we are solving the differential equation term and partial differential, so once the x term, the space term with a second order space term, then there will be a single negative, and once there is a second or fourth order term, then there will be double negative will come, because second order spatial term means it will have 2 degree of freedom primary. So this will have a 2 degree of freedom. So this is 2 DOS 1 and 2. So how many forces, corresponding forces? There will be 2 forces. One force will be automatically negative, one force will be positive. Here once you will do, you will have 4 DOH. So there will be the 4 forcing term. Force means here bending moment and shear force both are force basically. Bending moment is also rotational force. So four forces term. So 2 will be negative. Okay, makes sense. So if you have 6, order 6, order 8, order 12, accordingly, that many number of negative we have to do. So that thing you have to keep in your mind that many number of negative will be coming. Okay. If that thing is not coming, you need to check somewhere you made a mistake. Okay. And you know that as we discussed in the last class that these sign convention are also dependent. Like for example, here if you see, like once we are writing these two equations that, just a minute, sorry. So that is my beam equation and bending moment equal to what we wrote? EI del 2W del x2 and V equal to EI del 3W del x3. That automatically implies my positive direction is this, positive this and this. So these directions are matched with these three sets of equation. Now if you change that direction, your either of the equation will be changed. Maybe either or maybe two equations will be changed. Okay. So make it consistent, and whatever the way you write the things, you can see that this change you can able to notice. Okay. Yes. So now what we do? So we can see that now with the degree of freedom. So these are my degree of freedoms. So these are the force. These are the displacement term, and these are the force term for the corresponding to the degree of freedom. These are the displacement terms, and these are the force terms. Left, right, left, right. Okay. Perfect. So what we try to do? We are try to take it in one side and try to write it. So here, if you see very carefully, we have e to the power of minus t, e to the power I omega t. Now think, why e to the power of I omega t is coming? So here actually, sorry, my bad, I made a small mistake. So you see, this is my degree of freedom. Okay. So you see, this has also e to the power I omega t, and this has also e to the power I omega t. So once we are writing this, we are writing uj left is equal to c1j plus c2j. Next thing, once we are writing ujr, that is equal to c1j e to the power of I beta jl plus c2j e to the power of minus I beta jl. Got that? Okay, fine. Why that e to the power get cancelled? I think you got that idea. Perfect. Because this is the amplitude. This first one is the total time domain response, and this is the amplitude of that time domain response. We are actually checking because what we have assumed? We have assumed that we are solving that full thing for under the harmonic excitations. So harmonic excitation has the frequency of I omega t. So that omega thing we are cancelling from both the side. Agreed? And in case of the force also, these are my force, these are the force. And importantly, what we try to do, what thing is unwanted and what is unknown also, and what we do not want. That is the C, C1, C2. So our target is to eliminate that C1, C2. So how we can do that? So we try to write the matrix. So first equation, from the first equation we write this matrix. That in the left side we are taking UJL and UJR, left side, right side, in terms of C1j and C2j. Make sense? No doubt. And also, and also for the beam element. Now, if we go to the beam element, we can see this is my degree of freedom, degree of freedom, degree of freedom, degree of freedom. Okay. So that degree of freedom again will be written in terms of A1, A2, A3, A4. Agreed? How we can do? Look, we did the same thing. W theta means the W left, theta left, W right, theta right in terms of A1, A2, A3, A4. Okay, that 4 equation we have written all of them in terms of unknowns and so we get a matrix here and we get a matrix here. Got that? Make sense? Good. So now once we get this thing, now what the next step? Now next step is that we are merging these two things. So this thing is coming here and this full thing coming here. Okay? Very simple. And what happened with the right hand side? Unknowns are also just added. And you can see that the equations are uncoupled. So we can see that this matrix is just going here and this matrix is just coming and sitting here. And what about that remaining part? They are completely becoming zero. Because there is uncoupled. Now if there is some coupling, then what would happen? Then we can see some terms here. Make sense? Agreed? Very good. Any doubt up to this stage? So yeah, so that way these things is coming. Then now next step, if we go, that is, now we are writing the force side. So previously we have done the displacement part. Now we are doing the force part. In the force part, what happening? Fj, FLR, C1j. Okay. We will get this and we will have these terms here, which is just nothing. If you just go back, you can be able to see these equations. If you are putting it, that will be coming exactly the same. Okay. Next one also you can put it the same way, that the beam part. So this is the bar part and this is the beam part. Again we are combining. So what it would be actually, like in the similar manner, this should come and sit here and this should come and sit here. Okay. And here also we will have similarly the terms, so that the first portion would have been same, because this one and this one will be coming actually here and here. That beta terms. No, sorry. My bad. And if these two row and column will be shifted, then these two will go here. And then remaining portion, AN will be nothing but same as this thing. Okay. So this change would have been done. Sorry, means that mistake happened. So now, if this thing happened, then what we can get? So if this thing happened, then we can get in the left hand side, we are getting FL, FR, then Yes, here also we need to pay attention. Now you see here. Okay, just let me do it properly. Just a minute. Okay, so you can see what, like once we are solving this thing, so first case we are getting HD. So this is basically HD. That means you are having your displacement vectors. So that is my D, basically D vector with this is the unknown vector. So HD matrix time unknown vector. So D vector is equal to HD times unknown, and this force equal to HF times the unknown. Okay. Now here one important point we need to notice. So what we can think generally? We can think that F should be equal to HF times, and so here we can write C equal to HD inverse times D. So instead of that C, we can write F equal to HF times HD inverse times D. That we can do, but we need to pay little attention. What? That is, this F and this D are those degree of freedom and the force terms are correlating or not. What I want to mean? Let's see the positions of each and every terms. This is my axial left. This force is axial left. So their position is correct. This is axial right. This is axial right. Their position is correct. So 1 and 2 are correct. This is my transverse up. This is my transverse. This is a shear force. So shear force is basically a translational force. This is correct. Then theta M. Perfect. W. So these are okay. So this is fine. So if this way we are writing it, so we need to cross check that thing. Because here you can see, once we are substituting this full thing, we generally try to do it like this way. Like once we are calculating it now. If you see, once you are calculating, first we are calculating M, moment. Because moment is the second order. Then the third order thing is the shear force. So often we try to put the first the second order, then the third order. So generally we wrote the moment first and then we wrote the shear force. But we should control that temptation. Okay. We need to check it where we are putting what. So that shear force should come first, then the bending moment, and accordingly those things need to be arranged. So if we arrange it properly, then we can write that our force vector should be equal to HF into HD inverse times D. Agreed? And this HF into HD inverse, that is what? That is the stiffness matrix. So this is nothing but stiffness matrix, but this is a little bit more than a stiffness matrix. Why? This stiffness matrix is also frequency dependent. And this has the effect of inertia as well. So that's why we can call it dynamic stiffness matrix. So this is a dynamic stiffness matrix, or often we call it as a spectral element stiffness matrix. Because this formulation is the spectral element formulation. So the stiffness matrix we obtained using the spectral element, that's the spectral element stiffness matrix. Okay. Any doubt up to that stage? So the prime points are where we have to take. So if I just summarize the full thing, we need to write the differential equation. So write the PDE of the system. So from here, what we can do? Express. Just if I just try to make a flow chart. Just a minute. So first is write PDE. That's the first step. From here, like whatever the expansion you do, so you can do the variable separation. Variable separation. Then assume harmonic solution. Okay. Then what? Also do the assume the harmonic solution. Then try to write the displacement d wave in terms of unknown and force d wave in terms of unknown. From here, invert the matrix and you will obtain the stiffness matrix. Got it? The way we have done that full thing. Okay. Now this thing can be implemented for many other cases also. Yeah. So any question up to that? Is that clear? Very good. So now this process can be implemented for much complicated also. Like for example, now if we do the 3D frame element, then what will happen? Now you see, previously we have how many degree of freedom? 6. Each node, 3 degree of freedom, 2 node. Now here we are having how many degree of freedom? 12. Yes, each node 6. So can you see from the equation of motion how the 12 degree of freedoms are coming? You know, locating. Again, there is a mistake. Torsion. Can you see the? Can you look at the degree of freedom from the equation of motion? How? Always see that coefficient order of x. First one, order of x is 2. 2 degree of freedom. Here order of x 4. Here order of x 4. Here order of x 2. Add how much? 12. So that total degree of freedom is 12. Okay? Very simple. Way to do that. Yes. So now once we will do that way, now obviously I cannot go in every day. So now you can understood that process, how it is working. So you can see that first one once we are doing, so that is my axial. So you can write u like ux into this, and ux can be written like this way. We have already done that bar element. Fine. Then beam element in the x. Like here, if you see how this thing actually happening, look. This one is torsion, this one is axial, and this is bending, this is bending. Okay. So this bending is about, maybe if I just name it like x, y or z. So this one is about y axis and this one is about z axis. So here one is about y axis and this one is about your z axis. But in all the cases, your variable is x. That is very important point. Your variable is x. Why? Why? Check the picture. Element is in x direction. There is no element in the y or z direction. Simply. Element is, that domain is in x direction only. that movement can be in y and can be in z, or yeah. So that's why we are writing it like displacement in the y direction, displacement in the z direction, rotation about the y axis, displacement about rotation about the z axis. But there is no domain in the z or y axis. So therefore, no equation in terms of the z or y. And you can see here also, once we are defining it, all are defined in terms of x. There is no question of y or z. So obviously, how z can come? No question. And then the torsion is this. So once we do that way, then what can we expect? It will give me a 12 degree of freedom, 12 displacement degree of freedom. We'll have 12 unknowns. Like you can see here, C1, C2, C3, C4, C5, C6, C7, C8, C9, C10, C11, C12. 12 unknown will come. 12 displacement degree of freedom. 12 corresponding 12 forces. Yes. So these are nothing but my displacement degree of freedom. Whatever you will substitute, 0L, 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 you can able to get that full B matrix there. So what will be the size of the B matrix? Anybody? 12 plus 12, exactly. That will be 12 plus 12. Agreed? Then this is the force. Correspondingly, forces we need to put. We need to check forces are matching with the degree of freedom. If they are not matching with the degree of freedom, it will be a problem actually. Okay? That thing we need to be sure. Here this will be also cos 12 cos 12. So now, simple thing. So this procedure become quite streamlined with this. But obviously that doing that inverse 12 plus 12 with the analytical inside is challenging. But in reality, you don't need to do that inverse like this way, because you can make the program in MATLAB or something, and if you are giving the value of omega, then these matrices will be known matrix. So you can able to evaluate them. For each omega you can solve, and each omega you can able to calculate what are the frequencies are coming. Okay, what are the smoothness matrix for each omega you can able to calculate. Agreed? It's nice. So if you do that 3D beam element, you can see that B matrix is somewhat like that. So you can see that this is typically the B matrix look like. B, H, you have to do B inverse. H into B inverse, that is this guy. Means, yeah, I did not also able to write that H matrix. These are the terms we have written. I did not dare to do that B inverse and multiply it. So you don't need to do that in fact actually. Okay. So do you have any question up to that? So these are straightforward ways to do it. Okay? But still here we see one important thing. That is what? If you see, look, matrix are primarily looking like they are uncoupled. Like, if you see, these do not have anything with respect to W. These also do not have anything V or psi. They are not coupled. They all are like segregated. Like they are not looking at other. They are just doing that thing. Okay. But reality is not that simple. So suppose, so that's why like try to introduce something where we can have the coupling. So this is one of the case where we can have coupling. Like suppose we have a thin walled monosymmetric beam. Now here you see, look, if you see the equation of motion, you can get a sense that the things are getting coupled. Look, H psi. Previously what was there? Like this thing only was there. Now here what happened? H and psi get coupled. Now here psi like fourth order, second order, and then H get coupled. So here that portion, like where you have a complete zero, that zero band will not get. You will not get that zero submatrices. Those zero submatrices will be gone. So it will be now more populated matrix. So this type of thing you can write. So we can write it in the simple way like this way. So these are actually some non-dimensional parameters. We need to introduce some cases some non-dimensional parameters, because otherwise the equation will become quite complicated. Okay. So in this, if you do, you can see that. So here the domain was y. I have taken it in the y domain. So you can write everything in terms of y. But it's not a big deal. Like, so that's why I just take it here as a y instead of x, because it not need to be always x. It can be y also, but everything will be y then. So this way you can write that full equation. Again, we are following the similar type of thing. Look, fourth order, what this. Here, now you can do a fantastic thing. Once we are having this type of coupled equation, we can try to go to a single variable. How? Think here. How the equation looks like. This is fourth order of H. This is zeroth order of H. This is zeroth order of psi. This is fourth order of psi. Second order of psi. Zeroth order of psi. And zeroth order of H. Make sense? Make sense? Now, you think, what should be the final degree of freedom? Let's revisit it. What should be the final degree of freedom? What do you feel? How much it should be the final degree of freedom? It tells 4. It tells 4. So 4, 4, 8. Okay. So here one thing we can notice, that if you do a substitution, we may able to resolve a lot of things. How that substitution we can do? We can think that this equation, that first equation, we can write it psi of y eta square equal to okay. So now you see here. So if you calculate the psi of y from here, and if you do the second derivative, what will happen? Here it will be like 1 by eta square. That will be sixth order, and this will be second order. And if I do psi 4, this one will be okay. Agreed? Why we can do that? Whether can we do that or not? Do you agree? I did it, but is it correct or not? Why it is correct? I just simply take dy in all the sides. I can take it. Okay. Now what I do? I just substitute each and everywhere these terms. Substituted this here, substituted that first one here, substituted this, and then so we can get this complete term, which is 8th order equation. What is the benefit? Is there any benefit? By the way, is it clear or not? Exactly. So first thing, I just calculated the psi. Then I found there is a psi to the power 4. Well, not psi to the power 4. Fourth order derivative of psi, second order derivative of psi, then psi. I just substituted everything from the psi in terms of h and its derivative. So now my full equation becomes in terms of h and their derivatives. Agreed? Agreed? Just a question. Can I do the integration? Can I do the integration in that same way? Like, for example, if I take the second equation, I do the integration 1 time, 2 time, 3 time, 4 time. Can I do that? Exactly. Very nice point. Constant will come. So integration is not allowed. You cannot do the integration like this way. You can only do the differentiation. That is a very, very important point you should keep in mind. If you are doing this type of substitution, you can only perform the differentiation, not the integration. Agreed? Got that point? Yep. So you can get a 8th order equation. What is the benefit of getting 8th order equation here? Fine. Previously, if you see 6th order, but we did not write any equation directly. 8 constants. 8 constant, okay. We will also get 6 constant last time. Yeah, whatever the equation, you will get that many equations, and we have also done that 12. So 12 constants also came. Where is the prime point? This will give a characteristics equation. So we can able to, like, once we are solving the natural frequencies, this thing can help a lot. And this is easier actually if we can able to make it like that complete broad equation. We can able to write it. So we can able to identify also how the degree of freedoms are connected with each other. Because now they are coupled. You can still able to solve it. Means you don't need to go like that way. You can just put h and all those things and you can solve it. Not a problem. It will also work. Very fine. No issue. But if you have a chance, you may able to go with this way also. That is the only thing like what I want to just put it here. But previous case, there is no chance. You will not have any scope to get that way the degree of, means you cannot able to get a single equation, higher order equation where like the 12 order equation you will not get because the degree of freedoms were decoupled. But here the degree of freedoms are coupled. That's why you can able to get a 8th order equation and you can able to write the full thing. Okay. And that shows the important point. That shows whatever the eigenfrequencies you will get, they are actually representing a coupled system. And they are not decoupled. Like suppose if you change the axial thing of the bar, in the previous case, maybe it is not affecting the bending. Although that is going to change. It's just like if you can imaginarily think, if you think like you can able to increase the A but without increasing the I. So then what will happen? It will not going to change your bending. Just like your axial is get increased. So that type of effect. So what will happen? You can see that the frequency is coming for axial is shifted, but your frequencies for bending is not shifted. But this type of thing is not possible here. Here this thing is coupled. So you cannot just do change one and another will not be changed. That is not possible. Here the full thing is getting changed. Make sense? So yeah, so I'm not going into that, like that full derivation and all those things, obviously understandable. Like, but so you can refer to the book and those things are very nicely done there. But primarily what we are trying to be. So if you see what primarily our objective, we have that full equation, 8th order equation, fantastic. So 8th order equation will give me 8 unknown and 8 roots. Okay. So I can write it in this form. Agreed? Now, I can say that these are the states. What is the, sorry, I forgot to mention the state. What are the states? States are actually, like for example, in case of the bar, states are the force and the degree of freedom. Means suppose displacement and force. These two things commonly are the states. So D and F. So in case of the B, states are vertical displacement, rotation, bending moment, shear force. Combined thing is the state. So 4 state. In each node you will have 4 state. Okay. So whatever the total degree of freedom, that many number of states you will have. So here we are having 8 states at each point. Okay. So 8 state, accordingly 8 state we can able to calculate. So one state is H itself, then psi, then theta, then all those things we can able to calculate. So 8 different things we can calculate. Okay. So among that 8 state, there will be 8 displacement and 8 forces. So 8 displacement, like 4 are for 0 and 4 are for L. 4 forces for 0, 4 forces for L. And we can just put our H. Please notice 4 minus. So that thing is very important. Will happen every time. If you write it properly, you will get whatever the order of the differential equation, half of that you will get in the force negative. Again the same thing. We just do and we will get whatever the stiffness matrix we get. Makes sense? So we got the stiffness matrix. Yeah, so you can get that in the book also. Now there was a nice point. So there is an important point what we were actually discussing. So we have seen that till now what we have seen that complete solution. So we can able to make the stiffness matrix or dynamic stiffness matrix to be precise. Okay. Now this dynamic stiffness matrix. So what is the utility of doing the dynamic stiffness matrix? Why do we want to make that dynamic stiffness matrix? So there are few important points. So if I try to think that dynamic stiffness matrix, question is why? So first and foremost important point is, like, let's say you are having a mass like this. So normally spring means you are applying a force K. You know how much is the displacement delta. If you are applying a force, if you apply a force F and if your stiffness is K, you can say your delta will be force divided by K. That will be your stiffness. Now just think that problem. You have a spring mass system. Now you are again applying a force F, but F is not a static force, F is a dynamic force. Okay. Again you will have some sort of displacement. Definitely. In that case, what will be your F by delta? Is it only K? Will there be no effect of mass? Or what? There will be complete injustice with the mass if there is no effect of mass. Oh, that's why you can think that if you do the free body diagram on that mass, then what we can found? M x double dot, and this will be k into x, that will be equal to force. So what can we write? Mx double dot plus kx should be equal to force. So we can say that here the force is, or maybe F I can write it. So F is equal to F into e to the power of I omega t, and X is capital X into e to the power of I omega t. Okay. Both are harmonic, I am just assuming. So if I do x double dot, that will be minus omega square x e to the power of I omega t. So I can write it minus omega square m plus k into capital X e to the power of I omega t should be equal to f e to the power of I omega t. So what is my x? So my x, so you can see in previous case it was a k into x equal to force, and now my k becomes minus omega square m plus k. So do not have any injustice with the mass. Mass is also have its role. And this stiffness is known as dynamic stiffness. And importantly, you can see dynamic stiffness matrix is dependent on frequency and mass. Exactly. Most important, frequency and masses. Masses, definitely we can see that we mentioned that mass is considering, but the most important point is frequency. So now you can think your stiffness is no longer dependent on the system property. Previously, K is the system property. K and mass are the system properties. So system stiffness was dependent on the system property itself. But here, system property is not only dependent on stiffness is not only dependent on the system property, they are also dependent on the excitation. Because omega is not the system property, omega is the excitation property. So that thing get, so here, so we can see that this actually tells us how much amplification will be happening due to some specific level of frequencies. If we are exciting it maybe in the 5 Hz, we can get some type of response, or the stiffness will be some different. And if we are having, like, maybe if we are exciting it at 10 Hz, our displacement will be something different for the same amount of force. This thing can be justified with the dynamic amplification factor. The dynamic amplification factor actually tells the same thing, because it get extremely high once your omega square m plus k, that becomes 0. That means the stiffness of the system becomes 0. So you are giving a force and the system is going, and you are getting an infinite response. And more importantly, here the damping can also be associated into it. So we can get a damped system. So dynamic amplification factor is actually encompassing that phenomena. Okay. So here, if we think, once we are taking a stiffness matrix of a beam, we may be recalling the Timoshenko's stiffness matrix. So that is basically 2lbi by L cube. Some matrices are coming like this. So 12bi by L cube, 6 ei by L square. So this way that full matrix is coming. I am not writing the full matrix. I can't remember also. So that way we can get that full matrix. Well, here it is 40i by L. That way that full matrix is coming. Fine. That is a 4x4 matrix. So here we had also, that is the my shear force, bending moment. And here we will have my displacement, and that is W1, theta 1, W2, theta 2. So this way we can able to get different degree of freedoms and we can able to get it. Okay. But important point is where once we are doing it. So here you see they are having no effect of density. There is no effect of density and no effect of the frequency. But once we are making the dynamic stiffness matrix, these things are present into it. That is the very, very vital point. You can see. Agreed? Any doubt? Any doubt after this? That in the dynamic stiffness matrix, that density term system. Now there is also another important things happening here. That is, once we are writing it in the dynamic stiffness matrix form, now think, like let's say we are maybe solving for the bar. I think in the last class we have done that. And if we are putting so once we solve the bar, what happened? Here the degree of freedoms are U1, U2, F1, F2. So we are having F1, F2, that matrix with U1, U2. Okay? And these are the dynamic stiffness matrix. So cos beta L minus 1, EA beta L sin beta L. Sorry, I should write it clearly. Just a bit. EAL divided by EA beta sin beta L. Agreed? Okay, fine. So that is my stiffness, means that a complete system if I write it. Okay. So there could be two possibilities. One case is we are trying to calculate the response. And what is beta? By the way, beta is rho omega square by. Very good. Yes. So that may have the two different cases. What are the two cases? First case is case 1. We are exciting the system with some force. Fine. And what will be the case 2? We try to see the free vibration. That is the free vibration. So free vibration means we try to find out the natural frequency. Okay. So natural frequency of the system. Okay. Now you need to see one important point, that once means for both the cases, another important thing is required, that is the boundary condition. Means we cannot just let it like this way. We must have some boundary condition to be imposed on the structure. Otherwise, we cannot solve it. Perfect. So let's say we just say that, okay, left side is, we have fixed the U0. So U1 is equal to 0. So the left side is fixed. So U1 equal to 0. So U1 equal to 0 means I can cut these two things. And F1 will giving me some sort of reaction force. So F1 will become nothing but a reaction force. So U2 can only be actuating the thing. So what will be my F2? So F2 will be equal to EA beta divided by sin beta L into cos beta L into U2. Okay, fine. Now see, if we are doing the free vibration problem, then what we can say? If we are doing free vibration problem, that means what is unknown and what is known. Think in this equation, what is known and what is unknown for the free vibration. Beta is omega. Yeah. So if I just go one after one, E is known. E is the Young modulus of the system, known. A is cross section, known. Beta, you can see that is rho and E. Rho and E knows, but omega is not known. So beta is unknown. Beta is unknown, and L is known. Here also beta is unknown, L is known. Okay. And U2, in case of the free vibration, we don't know how much is the displacement, and we are not bothered with that. We can just say, because there is no force actually, it's free vibration. So this thing should be equal to 0 for the free vibration case. So what can I say from here? E beta divided by cos beta into sin beta L should be equal to 0. That's the condition coming from the free vibration. Agreed? Now we have seen that EA cannot be 0. Forget. So what we left with? Beta into cot beta L, that is equal to 0. Interesting. Beta into cot beta L, that is equal to 0. How it can be possible? So let's plot the cot beta L. How cot beta L look like? So here, solving this type of thing, what we have to do? We need to plot it. Beta into cot beta L. How does it look like? So once they are becoming 0, we can say, and able to check that how the solution is set to be coming. So we can write a small MATLAB code. So you can see here, that is, I'm just taking that beta. Just I take a like a variable like 0 to 10 with the 0.001 increment. Then y, that is equal to beta multiplied by cos beta divided by sin beta. Okay, and I'm first plotting it with respect just beta with y, and then I plotted beta with the log of y. So first graph, if you see what happens, you see that it is going and you have a very sharp jump, then again sharp jump, again sharp jump. These are actually very difficult to identify where exactly you have the solution. So that is why it is very much wise idea. And you see also that solution is went up to 10 to the power 4. So finding out the solution exactly where the beta value it is coming to 0 is really very difficult. So that's why it is always advisable to plot it with respect to the logarithm. So logarithming helps in what sense? Once we are plotting that y in terms of the tail log and we taken the absolute of it, then once it is becoming close to 0, then this one is going to almost like a negative infinity, the logarithmic value. Because that's a very small value, and taking the log of that very small value is becoming almost like minus infinity. So wherever we will have this drop, these are basically the natural frequencies of that system or the solution of beta. I should correct myself. There is a solution of the beta. Okay. So here you can see what are the solutions. Maybe someone can take a note. 0.1571, 4.712. Third one is 7.854. Okay. Now let's see. Just tell the second one. 4.712 divided by first one. 571. It's almost 3. Okay. Just do the other one. That is the third one. Tell 8 point. 854 divided by the first one. 1.571. Almost 5. So that means what we can see, that they are the integer. And what is 1.71, 1.571? Just check it. 1.571 divided by 3.14. This half. So that is nothing but pi by 2. Okay. So what can I get? So if I just assume that L is equal to 1 and beta equal to quad beta L, that is equal to 0. So I can say, quad beta that is equal to 0. So I can say beta is equal to pi by 2, 3 pi by 2 and 5 pi by 2. Like this way this is going. If I take more and more, I will again get drops. That way. Now what is my frequency? So my frequency, if I substitute it, that is omega square equal to E by rho into pi square by 4, or maybe I put n square pi square by 4, where L is equal to 1. Okay. Makes sense? So this way we can able to find out what is the natural frequency of the structure. Does that make sense? Important point. How many frequencies we are getting? That is basically infinite number of frequencies. Here, once I make it, I do it up to 10 only. If I make it 100, much more. If I make it 1000, much more. So it is basically infinite number, endless number of frequencies. Is it correct? Okay, let me rephrase the question. If we have a multi-degree freedom system, then how many frequencies should we get? Number of degrees of freedom. Okay, perfect. So if I analyze this system as like, let's say, some of the lumped masses, like this, then how many then as many number of masses we are dividing it, we should get the degree of natural frequency is that many number, not more than that. But here we can think that once we are solving it as a continuous system, it is becoming very small number of very small elements we are actually taking, and that's why it's become a continuous type thing, and we will get infinite number of natural frequencies. Make sense? Another important point. Once we are having the natural frequencies, there is also another additional thing always associated with the natural frequency. That is mode shape. Exactly. What is the mode shape of it? It's a very obvious point. Once there is a natural frequency, there should be a mode shape. So what's the mode shape? So okay, what is the mode shape? What does it mean? That is the displacement field. Can we get the displacement field from here? If you see, once we were solving it, We'll just go back quickly to the bar equation. That's my bar. UJL equal to 1 1 C1J. This is C2J. Okay. What can I write? This is, please remember these two. So I can write it. U2 will be one one e to the power of I beta L e to the power of minus I beta L C1 C2. Am I right? We check. Actually, sorry, I wrote it wrongly. Yeah, I should take this one. Sorry. I should take this one. Like C1, is it I beta or only beta? Is it I beta or only beta? I beta. Okay. Just a minute. So if I think U of x equal to, how we can write it? U to the power of I beta x C1 e to the power of minus I beta x C2. Okay? Agreed? Good. If we are agreed with that, we have also written U1 equal to e to the power of I beta 0 C1 plus e to the power of minus I beta 0 C2, that is nothing but C1 plus C2, and U2 will be equal to e to the power of I beta L C1 plus e to the power of minus I beta L C2. Okay? That is so I can write it U1 U2 will be equal to 1 1 e to the power of I beta L e to the power of minus I beta L U1 C2. So C1 C2 will be equal to how much? So what is AD minus BC? So AD minus BC will be okay. So that thing will be coming here. Okay. And what is coming here? That is AD. So e to the power of minus I beta L. C is changed.
BC or mutations?
BC is not in touch, na?
Just negative.
Just negative. Okay, fine. Thank you. Yes, is it correct? So what is my C1 now? Now my C1 will become 1 by e to the power of IBL into e to the power of minus IBL U1 minus U2, and C2 will be equal to okay. So if I substitute my U of x, that will be how much? E to the power of IBX into C1 into C1 plus and now okay, another important point, my u2 is u1 is 0, so forget the u1. You see my u1 is 0, so if I just forget the u1, what can I get? One by minus IBL minus I beta L u2, so minus sign, and this one will become u2 with a plus sign. Okay, so simple. And this into u2. So P1 IBX is into u2 minus plus to the power of minus IBX. So what can I write? So that become my shape function. So we can also see it in nice manner. Minus I beta x minus beta x divided by to the power of I beta L. So if you see e to the power of I beta L minus, what is the meaning? Cos beta L minus I sin this thing is a constant value because beta is also known for different frequencies. What are the betas known to us? And this beta is also known, and this is x is vary. So that way we can able to get the different mode shapes. Or that. This is called solving eigen. This is we got the how the displacement, how the deformation modes should look like. What are the eigen modes? We get the natural frequencies and we also get the mode shapes. Both the things we got it from. So you can do it for any of the things. You can get it like this. What is a deformed shape? Yes, deformed shape we can get it. Means deformed shape will be coming after multiplication. This is just the giving the shape, but not the value. Yes. So each of the cases that shape will be different. Okay. Make sense? Ha. So suppose if we just put it in our case, L we assume 1, beta was coming how much? Pi by 2 3 pi by 2, 5 pi by 2. So if I just simplify it little further, means if I just think this portion is just a value, this portion is just a value. So my main thing is this. So sine, first thing is the pi by 2x. Then second thing, 3 pi by 2x. And third thing is sine 5 pi by 2x. How they should look like? How sine pi by 2x, sine pi by 2x looks like? Think like you are going up to this. So yeah, L equal to 1. So maximum you can go up to 1. If you go up to 1, then pi by 2. So maximum value will be pi by 2. Sine pi by 2 is 1. It will become then sine 3 pi by 2. In 5 pi by 2. So these are the shapes you will get. Okay. Got it? So this thing we can solve once we are doing the pre-vibration. Now what about the case 1? Okay, by the way, any question up to that? In the case 2, pre-vibration, natural frequency. Any question? No question. Okay. So now if we think, in case of the forced vibration, the things is much more easier. Why? In forced vibration, actually what happened? We are giving some excitation that if we know what the frequencies we are exciting, that omega is also known. So omega is known, that means beta is also known. Okay. So what we are solving U2 basically. In that case, U2 will be how much? U2 will become our F2 into 10 beta L divided by EA beta. Simple. We know omega, what omega we are exciting. From omega we can calculate whatever is the beta. For that beta we can solve it. So we will get what is the U2. Easy? Perfect. So forced vibration is simple in this case. But pre-vibration is really complicated and it has a lot of the different things. But forced vibration can be complicated if we are not exciting with a single frequency. If we are exciting, like let's say we put a earthquake motion, where we cannot able to decompose it into a proper frequency domain or some things. Those, yeah, you can say that, okay, I will do the FFT and do it. That's possible. I'm not disagreeing. But if you try to solve it like for any type of excitation, those cases, it will become difficulty. Oh, yes, please.
Sir, you were in acceleration actors. So how the is
Yes. Yeah, very good point. Very good point. This is a displacement field. I am just drawing the values. This is a very good point. Your confusion, I think, is in that how it is going up. This is just plotting. I am plotting the values, that how much displacement is happening. You got that thing? How can I plot that if I not plot it in that vertically? It is just the plotting only. Okay. It is not that the things is going that way. No. It is just the plotting. Okay. In case of beam, you can see it is flapping like that. But here it is just like it should be in the x direction. It will be elongated. Now, how much elongation is where? You cannot plot it in that same direction. That's just like I plotted in that, like whatever is the like increment is happening in the x, I just rotate it into y and just plot it. But that's a very good point, actually. Got that, everyone? Perfect. Yes. So there was a very nice question comes that, okay, coupling we can see from the equation, but how in the real life we can able to understand that whether there is a coupling or not, instead of going into the equation. Very nice point, actually. Very nice point. So now here you need to understand one point. Like for example, if you see this structure like monosymmetric beam, here you can try to think that, like if you are applying some type of like bending, are you getting anything in the axial direction? If you are getting some movement in the axial direction, and more importantly, if you are considering that in your equation, then definitely your system is coupled. But if you are not considering it, if you are neglecting that, then they are not coupled. Okay. So those points are important, actually. Like for example, if you think if you are applying load somewhere here, what will happen? It will get torsion sometime, and that can produce some sort of bending. So bending, torsion get coupled. You cannot distinguish these two things here. So this type of phenomena you have to actually understood. Now, once I told about the bar and beam like a frame element, if you see normal equation, it tells like they are not coupled. But if you make the thing like a little bit curved, they will be coupled. They will be coupled. You cannot solve the things without coupling. So, and more also there is an important point, whether you are considering that effect or not. Often for the simplicity we ignore that coupling type thing so that our life becomes easier. So yeah, in that case it is fine. You may neglect it, but so prime point is that if you are applying some load in the other direction and you are getting the response in the other side, you can say they are coupled. Otherwise, they are not. Okay. Anything else? Anything else? Okay. If not, then I would like to thanks to all of you.